So today it is my true pleasure to introduce Jenna Wiens, our speaker. She is the Morris Wellman Assistant Professor of Computer Science and Engineering at the University of Michigan in Ann Arbor, and her primary research is at the intersection of machine learning, data mining, and healthcare, so clearly relevant to this group. The overarching goal of her research agenda is to develop computational methods that we actually need and can use to organize, process, and transform data into knowledge that we can act on. She got her PhD from MIT in 2014. In 2015, she was named part of Forbes 30 Under 30. She's got a major National Science Foundation Career Award, and she was recently named to the MIT Tech Review's list of innovators under 35. So we are very fortunate to have Jenna here with us today. So without further ado, Jenna.
Thank you so much for inviting me to come and speak today. I probably don't have to tell a room full of Canadians this, but this title was inspired by the popular CBC podcast that I grew up listening to, White Coat, Black Art. It's a riff off of that. So in today's hospitals, we're collecting just an immense amount of data, everything from diagnoses and medications to imaging data and notes. And in my group, we develop and we use machine learning techniques that can identify patterns in these data, patterns that can be used to sort patients from low risk to high risk for a particular adverse event or bad outcome. Given the challenges that today's healthcare systems are facing, these sorts of clinical decision support tools are critical. So what do I mean by the problem? Well, for one, currently the demand for clinical care far exceeds the supply. And economists anticipate this is only going to get worse in the near future. By the year 2025, we anticipate a shortage of over 100,000 physicians in the US. And this shortage exacerbates what's already a serious issue in the field, clinician burnout. When you talk to clinicians today, they cite the increasing computerization of the field widely as a problem rather than a solution. Physicians are spending more and more time entering and studying data about their patients while still ignoring the vast majority of it. And this burnout, combined with a lack of tools to make sense of the data, has contributed to a large number of medical errors. A study published in the British Medical Journal in 2016 estimated medical errors as the third leading contributor of death after heart disease and cancer. All of these issues combined highlight an important need, but also an opportunity for AI. For example, in our own work, we've shown how machine learning tools can be used to identify which patients are at greatest risk of acquiring an infection during their hospitalization. We focused on predicting infections with Clostridioides difficile, or C. diff, which is a bacteria that takes over the gut when normal flora get wiped out. It's associated with significant costs and morbidity. And we hypothesized that one of the reasons that this infection remains so stubbornly prevalent in hospitals today is because we lack an effective tool for measuring patient risk. So using existing data that's already being collected through routine clinical care and the electronic health record, we built a model to predict which patients were at greatest risk of acquiring an infection during their hospitalization. And we showed that this model could identify patients 5 days in advance of clinical suspicion, so before a test was even ordered. Once deployed, such clinical decision support tools could be used to help guide interventions, whether it's targeted environmental cleaning or even whom to test. And this in turn could lead to decreased length of stay, decreased transmission, reduced costs, and ultimately improved patient outcomes. But we're not stopping there. So the data and the techniques that we've been using to predict healthcare-associated infections can be used to predict other inpatient outcomes, like acute respiratory distress syndrome, graft versus host disease, shock, and ARF. And now that many hospital systems have been collecting EHR data for a decade or more, we can also start to look at the trajectory of diseases and study how patients with Alzheimer's disease evolve over time, or even go beyond the hospital, looking at data collected from wearables like continuous glucose monitors to study chronic diseases like diabetes, or collect samples outside the hospital and microbiome to study diseases like cystic fibrosis. And I'd like to just pause here and acknowledge all of my clinical collaborators. So my team sits in computer science. We're computer scientists by training, but none of the work that we do would be possible without our clinical collaborators. I don't think that there's a day that goes by where I don't meet with at least one of them, and they're really crucial to guiding us and keeping us on track. So while we're motivated by really important clinical problems, ultimately we're interested in solving the technical challenges. So making AI work for healthcare. And from a technical perspective, there's a seemingly unlimited number of challenges. And in my lab, we work across a number of different subfields within machine learning, with an emphasis on time series analysis, regularization techniques, and deep learning. So while the potential for machine learning in healthcare warrants genuine enthusiasm, the limited adoption to date suggests that we still have a ways to go, right? In addition to increased risks and responsibilities associated with working with health data, there are also unique technical challenges related to model interpretability and small sample size. And today, in the remainder of the talk, I'm going to dive in to both of these issues and talk about some of the methods and techniques we're using in my lab to address these challenges. All right, so starting with interpretability, in healthcare, many users seek interpretable models, models that can tell a user not only who's at risk, but why a patient's at risk. And oftentimes this allows users, say a physician, to check the model against his or her intuition. So to achieve interpretable models, many will focus on limiting the size of the rule set, since if I can tell you why a patient's at high risk with 10 variables instead of 1,000 variables, it's inherently more interpretable, and the average complexity of the rule, so linear models instead of, say, nonlinear models. Arguably, the simplest models to understand are traditional handcrafted risk scores. And here I'm showing you an example from the TIMI risk score for non-ST elevation myocardial infarction. And it's based on 4 historical questions and 3 present questions, each of which contributes a single point. So you can calculate this just in your head. And this is both interpretable to the user, so the physician who's going to compute this, but also to the people who designed the model. Okay, so you have those 2 groups. And while interpretability has been deemed important for the physician and the people who are going to use the model, we see it as being really important to the people who are actually building the models. Okay, they allow ML researchers to check the model. And I'll give you an example from our own research. So we are looking at predicting risk of mortality in a patient population with acute respiratory failure. And I was working with a pulmonologist in critical care and 2 undergraduate researchers over the summer. They were both computer science undergrads. They had just taken the machine learning course, and they got a set of labeled data, and they trained a model to predict who was at greatest risk of mortality. And they came back, and the performance of the model was really good, and they're really excited that they had already solved the problem. We were only a couple weeks into the summer. And I asked them to go back and train a model that we could actually look at, well, what were the most important risk factors? So they came back to me with the most important risk factor, and they said, well, it's this medication here, scopolamine. This is what is really contributing to increased risk. So we went to our clinical collaborator, and we presented this information, and he said, well, that's a drug that's used almost exclusively in comfort care measures settings only. So you're not really, so the model didn't learn something wrong, right? It learned a correct association, but it didn't necessarily learn anything useful. So once we were able to query the model, identify what was driving its predictions, it was simple to just exclude patients who were on comfort measures only from our study population. So we were able to fix it. So it might seem like the arguments for interpretability are sound, but there's still ongoing debate in the community, and in particular in NeurIPS 2017, we hosted the first ever NeurIPS debate in which Rich Caruana from Microsoft Research, representing one side, and Jan LeCun from Facebook AI, representing the other. And the debate lasted nearly an hour. The whole thing is on YouTube, so you can find it. But I'm just going to play you a few key segments from each side. So listen carefully.
We now think that you just won't know about these problems. You wouldn't have anticipated them in advance if you can't sort of open up your model and see what's happening. So we think interpretation is very, very important for these models, or else the model is just going to learn new things. Interpretability, so it's not that interpretability is completely useless. It's not really useful. First of all, the vast majority of decisions made by automatic systems, so we know that the actually wants to be. Now, there is a small number of domains where interpretability is not only useful but required, like legal decision-ability, and OpenC for certain types of legal decisions. So that's the example these patients talking about. You just can't trust performance on a test bed in many domains, especially when you're intending to use a model or something that's sort of causal or contextual. You didn't evaluate the model value, you treated it perhaps, so now you're going to have to do something different. And we just find that every time we put on this magical access and see what's inside the model, we find an amazing number of things that are beautiful, do really make the model like accuracy. But we also see things that are very surprising, very disturbing, and then no human could ever let get deployed. And it's just so important to be able to put on magical access and it's easy.
Machines are going to make mistakes until they have the same kind of knowledge that we have, until they get common sense. And so that would be an argument to be careful and you won't know.
All right. So in the end, Jan LeCun concedes, well, he actually conceded pretty early on in the debate that interpretability was really important for certain domains, including healthcare, in part because AI lacks common sense. And this lack of common sense isn't relegated to black box models. So you're not free with interpretable models. Interpretable models can still lack common sense. I'm going to give you some examples. So this lack of common sense can lead to strange behavior that might go unnoticed. So for example, consider an image recognition task in which you want to identify or classify images as containing a dog or not. And suppose your training set is biased in such a way that every time you see a dog, there's also a frisbee. Now the model will correctly learn an association between the frisbee and the labeled dog. But what you want it to really pick up on is the fact that there's a dog there, right? It's just the correlation between the frisbee and the dog that's throwing things off. And the same thing can happen in healthcare. So if we go back to our model for predicting those healthcare-associated infections with C. diff, and we look at the top risk factors, we can start at the top of the list, and we see things like a diagnosis for C. diff infection in the past year. And this makes sense given that 20% of cases will relapse within 60 days. There are other proxies for the severity of illness of the patient, but you don't have to go too far down in the list before you start to see some puzzling features. And it could just be that this variable is highly correlated with another variable that is known to increase risk as C. diff. This is like the frisbee in the model. But given that there are known risk factors of C. diff, we sought to develop techniques in which we could nudge the model towards paying attention to those known risk factors instead of these correlations, right? So nudge the model towards paying attention to the dog instead of the frisbee. So I'm going to go into a little bit of math here, but to get everyone on the same page, I want to set this up with some background. At the end of the day, most machine learning problems are based on an optimization problem in which you have a loss function L that you're trying to minimize. So you can think of this as, maximizing accuracy, you're trying to minimize loss, the number of errors that you make on your data, subject to some regularization penalty, okay? And this is going to control how complex the model is and help reduce the possibility of overfitting, just memorizing the data. And we can reframe this as a constrained optimization problem, just moving that regularization penalty into the constraint. And if we use a constraint like L2 regularization, we can visualize it. Okay, and what this optimization problem ends up looking, we have the circle there is the constraint, so that's the L2 ball, and my loss function there, those are the red contours. So I'm trying to find the minimum of that intersects with that L2 ball. So if I have a really simple problem, so let's make this a toy example so that we can visualize this, where I have only two parameters. Okay, so only two input features, x1 and x2, and I'm trying to learn how to weight them. I'm trying to learn the theta 1 and the theta 2, how important they are. But if x1 and x2 are perfectly correlated, so x1 equals x2, then I end up with my loss function being essentially a line. Okay, a line where the slope is just -1, and I have some offset determined by c. Okay, so I'll achieve the same loss no matter where I am on that line. But again, because of that constraint, I want the solution to end up at the intersection. Okay, so what that means is I'm going to end up with theta 1 equaling theta 2. So there are different types of regularization that are commonly used. There's L2, the one I just spoke about, but then there's also L1, or lasso. And lasso is often used when you want to reduce the number of features, the number of input variables, to a small set. But the issue with this, while it encourages sparsity, meaning that it will learn to weight just a few of the parameters, it can randomly eliminate a feature. So you'll end up likely at just one of those corners of the L1 diamond. So instead of setting theta 1 equal to theta 2, theta 1 could be 0, and you have some weight on theta 2, or vice versa. Okay, so this is where you can end up with vitamin B being really important and some other important risk factor getting a weight of 0. And that leads to confusing behavior and confusing results. So what we sought to do is change this optimization problem to include domain knowledge. Okay, so tell me which risk factors you believe are important. And we encode that as a vector R, which tells me just a binary variable, 1 or 0, for whether or not that variable is known to be important. This is my expert knowledge, 1 for known, 0 for unknown. This is work done by one of my PhD students, Joshua and Wang, and it was presented at KDD in 2018. And we formulate the regularization penalty in such a way that we split the data into two, or we split our input parameters into two sets, those that are known to be associated with high risk and those that are potentially associated with high risk but are yet unknown. And then just to go back to the previous plot, we end up, if we plot the contour of this constraint now, it ends up looking like an eye, so we call this the eye penalty. And now you'll see that the intersection of that loss function with the penalty ends up right at theta unknown equal to 0 and theta known equal to some non-zero value. Okay, this is when you have two variables that are perfectly correlated. It will tend towards the known one. It has a number of nice properties that I won't go into detail with. But essentially, this penalty, this regularization penalty, favors a solution that's sparse in the set of unknown. Okay, so I'll have that small number of variables that are important, but dense in the set of known variables. So we ran experiments going back to the C. diff problem to see how well this worked. And we compared to a model where we used expert features only. So we sat down with clinical collaborators and asked them for a list of known risk factors for C. diff, and then trained only on those factors. Okay. And here I'm showing you two measurements. This is the performance of the model on held data. The average precision here refers to how often those known risk factors trickle up near the top of your list when you look at the importance of the features. So because I only have known risk factors in my expert model, the average precision is trivially 1. But the area under the curve, this is the discriminative performance, so how well my model is predicting is substantially worse. So 0.5 is no better than random, and this does about 0.59. So that suggests that you can't just limit it to expert features only, right? There are things we don't know that we should be including in the model. So when we use the I penalty and we throw in all of the features, the area under the curve goes up, right? Telling us that experts aren't familiar with all the risk factors. The average precision drops. Okay, so not all of the known risk factors will trickle up near the top. However, it's an order of magnitude better than other common regularization techniques like lasso, weighted lasso, or even elastic net. All right. And you can find, if you want to start training models using this regularization penalty, you can find all of our code on GitHub. You can also find a link in the KDD paper. Okay. So backing back up, to wrap up our discussion on interpretability, it's important to understand that it's neither necessary nor sufficient. Okay, many researchers cite examples of black boxes that they use in healthcare all the time. So oftentimes clinicians will say, well, I use a digital thermometer every day and I don't know precisely how that works, but I still trust it. And an argument to that is that, well, the people who built the thermometer do know how it works, right? The manufacturers know how they work. But there are also situations where we don't know why something works, right? There are particular drugs that we might be using. We don't have precise knowledge as to why that particular drug is effective, but we still use it. But we use it only after it's been thoroughly vetted, having gone through several stages of clinical trials. And we can do the same thing with machine learning, and actually this is what Jan LeCun argues for in the debate. But these studies can take years, right? And they're not without cost. They're labor intensive and expensive. So my argument is that to the extent possible, we should be doing all we can to vet the model in advance. Right? Look at those factors, try to identify label leakage, try to identify how you might have to refine your study population, right? Find that scopolamine or that frisbee that's throwing your model off. And it's tremendous, it's a lot easier when you're working with interpretable techniques. All right, so beyond interpretability, there's the issue of small sample size. And machine learning and deep learning techniques in particular benefit from having a lot of data, learning from a lot of samples. And this is an argument for collecting and sharing more health data in healthcare. But there are certain diseases or outcomes that are so rare, even if we had data on every patient in the world, it still might not be enough to draw inferences from the data alone. So what other fields do when they have this issue is they'll look for invariances in the task. Okay, so an invariance is a transformation that you can apply to the input that doesn't change the output or the label. So you can think of it as if I'm, again, trying to classify images of dogs, and I have a label for a particular image that tells me there's a dog there. That label won't change if I slightly shift the image. Okay, so there's some spatial invariance where it's still a dog no matter where the dog appears in the image. So what kind of invariances hold or do not hold for tasks involving health data? And how can we efficiently exploit them? Do existing techniques apply? In short, no. Okay, health data are different. And we need to rethink some of the techniques that are used. So I'm going to describe briefly 2 projects on learning what invariances are present in health data, and then also what invariances aren't present in health data. So starting, so many, many different types of health data. A data type that we work with frequently in my group are clinical time series data, and waveform data are an example of that. So here I'm showing you ECG. Waveform, so capturing the electrical activity of the heart. And you might want to take these data and set it up as an arrhythmia detection task. So here I'm showing you an example of ventricular tachycardia, or VTAC. And just below it, I'm showing you another example of VTAC. And the only difference between these 2 examples is that one is shifted. Okay, relative to the other. So this suggests that there is, at least for some tasks, some notion of phase invariance present in these tasks that could potentially be exploited. And again, going back to working with natural images in the computer vision community, often what people will do is they'll exploit spatial invariance either through this precise architecture of the model or by augmenting the data. So they'll take their images, their training set, and they'll flip them and rotate them and crop them and increase the amount of data. But with health data, we have many, many types of data. So we have lab results, medications, waveforms, notes. And when you sit down and you ask clinicians, well, how do I flip, rotate, or crop a patient? You don't get an answer. Right? It's not clear what invariances are there from the beginning. So data augmentation isn't straightforward. So again, inspired by the computer vision community, we set out to try to learn the invariances directly from the data. And similar approaches have been proposed for image-based tasks. So here I'm showing you the original image on the left. So this is from the MNIST data set, where it's a data set of handwritten characters or digits. So we can see a 5 that's slightly rotated, and we learn to transform that 5 to reduce interclass variance. Okay, so that now all the 5s look more similar to one another, and it's an easier task. We're going to do the same thing, only we're going to do this just in the time domain. Okay, we're going to learn to actually transform a signal. So you might have a time series of, say, blood pressure measurements or heart rate measurements, and we're going to learn how to transform them. So our approach is based on a sequence transformer network composed of multiple 1D convolutional layers. If you don't know how to read these, that's fine. I'll give you the high-level points, which is you input the signal that you're trying to classify as, say, high risk for mortality or not. And this will output 2 parameters that dictate the type of transformation to apply. And these types of transformations can either shift the signal left or right in the time domain, or up and down in terms of magnitude, or stretch or compress the signal in either direction. These parameters dictate the transformation that's then applied to the signal. We get our output, and now this transformed output can be input into my classifier. And you can use your favorite machine learning classifier. So here I'm just showing you a toy example. So the original signals are on the top, and I'm trying to classify blue versus red, where blue is a decreasing sine wave and red is an increasing sine wave. And I've added a little bit of noise here, and we can see that the original signal had shifts in it. Okay? And what I'm showing below are the transform signals. So here I'm learning how to transform them such that it makes the classification task easier. So again, at the top were all the original signals, and then I've learned to reduce some of that heterogeneity or variance within each class that makes the task easier for the next part of the classifier. So we applied this to a benchmark clinical task that's often used in the community. How many of you have heard of MIMIC, the MIMIC database? Okay, good. So it's a publicly available database. People have used it to look at a number of different tasks. A benchmark task that we looked at was predicting in-hospital mortality using data from the first 48 hours of a patient's intensive care unit stay. So we use the same study population train validation test splits as published by Heriton and al. And we looked at 17 features. So again, the same features that were previously looked at: heart rate, respiratory rate, et cetera. And we used our sequence transformer approach, and we compared that to an approach where we just used the original signals. So we didn't learn to transform them. And we compare these two models in terms of the discriminative performance, in terms of the area under the receiver operating characteristic curve, and the area under the precision recall curve. And compared to the baseline model that didn't do this transformation, we're able to get a slight improvement in both of these measures. And what was interesting was when we looked at just transformations that were applied along the time axis, or just transformations that were applied along the magnitude axis, we were able to get a small improvement with each. But it was the combination that led to the larger improvement. So by removing label-independent temporal variance, patients with similar outcomes start to look more similar, and the classification task becomes easier, especially when you have limited data. So we're really encouraged by these results, and as a next step, we're going to look at learning other types of transformations like local scaling and local warping. Again, if you want to play around with our code or train your own sequence transformer network, it's available on GitLab. The full paper was published at MLHC 2018, and it's also available online. All right, so beyond learning what invariances are present and can be exploited, it's equally important to understand what invariances aren't there. So this brings me to the last part of the talk, in which we explore methods for effectively modeling time-varying relationships. So here, when I say time-varying relationship, what I'm referring to is the relationship between X, some input covariate, and Y, the label or outcome, over time. And this can shift over time. So for example, the variables that put a patient at high risk for C. diff infection at the beginning of the visit could vary from the variables that put a patient at high risk for infection at the end of a visit. Okay, at the beginning of the visit, it might be things like, well, what medications were you on at the previous visit, your history. Once you've been in the hospital for, say, 7 days or 2 weeks, it might be more what's happening right now. So we looked at trying to learn these time-varying models, and in theory, long short-term memory networks, or LSTMs, should be able to learn these time-varying relationships. And if you haven't seen LSTMs before, that's fine. The real takeaway here from all these equations is that we're learning a set of parameters. Okay, just like in logistic regression, where we're learning parameters like theta, how to weight each input, we're learning parameters here, W and B. And the important thing in LSTMs, or what makes them so attractive in many cases, is that the parameters are shared across time. Okay, so at each time step, I can input, so each time step you can think of as being maybe a day in my model, where I'm going to input the variables for today and get a prediction. At each time step, the variables are the same. Okay, not variables, the parameters are the same. Same W, same B. And we hypothesize this parameter sharing actually makes it more difficult to learn that those time-varying relationships, which we hypothesize arise in a number of clinical tasks, especially when the sample size is small. So another way to learn time-varying relationships is to just break that and have different parameters at every time step. Okay, a different W, a different B at every time step. But you can imagine that if I'm making predictions, say, every hour, in 48 hours, my parameter space is going to explode quickly, right? It will grow linearly with the number of samples that I'm putting in. So instead, we proposed a mixing approach in which you learn perhaps 2 sets of parameters, so W1 and B1 and W2 and B2, and then at each time step, you just learn how to mix these parameters. So you learn how to average the parameters so that you can end up with different parameters at each stage or at each time step without having the burden of learning all those parameters at once. So we call this mixed LSTM, since it's a mixture of LSTMs, and this essentially relaxes the parameter sharing. And we hypothesize that our method would outperform an LSTM when you see temporal conditional shift, or you have these time-varying relationships. So again, we applied this to 3 clinical prediction tasks. The same task as before, in hospital mortality, but we also added 2 additional tasks. So we looked at predicting acute respiratory failure, the need for respiratory support with mechanical ventilation during the ICU stay, and shock, inadequate perfusion, which we quantified as the receipt of vasopressors during the stay. So to test our hypothesis, we first had to demonstrate that there were these time-varying relationships, and sharing parameters every time step was not the right thing to do. So here on the x-axis, I'm showing you increased parameter sharing. So all the way at the right is the equivalent of just the vanilla LSTM, and all the way at the left is the equivalent of if you have different parameters at every single time step. The y-axis here is the discriminative performance. And the important thing to note is that we see a peak somewhere in the middle. right? So sharing everything isn't the right thing to do, and sharing nothing is also not necessarily the right thing to do, especially for this task of shock. We saw similar relationships in the other two tasks. So this suggests that this shift is real and does occur in several different clinical tasks. So again, to measure the performance of our approach, we compared to a baseline LSTM, this model that shares everything, to our mixed LSTM that relaxes this weight sharing. And we showed on a held-out test set for all three tasks, mortality, ARF, and shock, we were able to get consistent and oftentimes statistically significant improvements over the baseline in terms of discriminative performance. So by relaxing, instead of completely eliminating weight sharing, we can improve the discriminative performance of these models in these tasks. And the paper, so this paper was published more recently. This was presented at MLHC just this past August. And it's available online. You can also find our code online if you want to start training your own models using mixed LSTM. All right. So this brings me to the conclusion of the talk. We spent a considerable amount of time talking about some of the technical challenges of getting machine learning to work for healthcare. But how close are we to actually augmenting clinical care with AI? So let's return to the beginning of the talk where I gave you this example of predicting healthcare-associated infections from electronic health record data. We published this work in infection control and hospital epidemiology in 2018, and we're now working towards deployment. And I spoke about this a little bit at the AI Deployment Symposium yesterday, but just to give you a quick overview, every day of a patient's admission, we make a prediction. We estimate the risk that that patient will develop an infection during the remainder of the hospitalization. And so every patient you get a curve that might look something like this. And step one was just integrating this into real-time data feeds. So to train the model, we use retrospective data, okay, going back to 2010. But now when we want to deploy it, we needed real-time data feeds. So we had to work with folks at the medical school and in IT to develop or to write custom web services to actually pull the data in real time. We did this and we launched in March 1st, 2019, and it's been running since then in the background. So for every patient, every inpatient at the University of Michigan Hospital, Michigan Medicine, we've been computing their estimated daily risk scores. And here I'm showing you a plot of the prospective performance. And I've got the retrospective performance, so how well we did in 2018 in the light gray, and the prospective performance in blue. And we see that it's tracking pretty well. We're encouraged by these results, but I can't stress enough how important it is to take the time to do this sort of prospective validation, since there can be differences between retrospective data and prospective data. And I talked a little bit about that yesterday. So our next step is actually using these risk scores to drive or help target clinical intervention. So we're working with our antimicrobial stewardship program team and our infection prevention team to design bundle interventions and deploy them in a targeted way. So in summary, there's a critical need for AI in healthcare, and by augmenting clinical practice, AI promises to reduce costs and medical errors through decision support tools. And it's critical that we start to build the necessary infrastructure to test these models prospectively and run efficient clinical studies now. And this is really the time to do this. And though we should proceed with caution, we shouldn't let black boxes stop us from making progress. I hope I've convinced you that interpretability is neither necessary nor sufficient. Black boxes might be okay if they've been thoroughly vetted in an environment that mimics how they will be used. And even interpretable models can lack common sense and trip you up. But this can be mitigated with domain expertise, the white coats. Domain expertise can inform our approach either through regularization techniques, so we can inject the models with domain knowledge, or through domain-specific architectures or information about what invariances might hold. Thank you. And I'm happy to take questions. Yeah. Yeah, that's a great question. So we do have a number of collaborators at other institutions as well. Michigan is close by, so most of my collaborations are there, but we also work with Massachusetts General Hospital in Boston, Rush Medical Center in Chicago, and many more. Right now, so the paper that was published in Infection Control and Hospital Epidemiology was actually both at the University of Michigan and at MGH. We showed that you could train a model using the same approach, even though there were different data, different EHR systems, different patient populations, different clinical protocols that worked comparably. Yes?
Just a follow-up on that question. Thank you for the talk. How long does it take to get models into practice?
A long time. Yeah, so I spoke yesterday, and I dove into far more detail about just the C. diff project, and I actually had a timeline there. And just the timeline from we have the model, so assuming you have the model, it's been retrospectively validated, to having the results from a clinical study and showing impact, we anticipate take about 3 years. We're hoping to shorten that. So a lot of that time was because this was the first time that we needed these real-time data feeds, right? So building that infrastructure. Now that we've built that infrastructure, we can reuse it. The nice thing about the model is that because we're not looking at really specific things, right? I didn't start with 12 curated risk factors. I just took all of the medications, all of the lab results. The infrastructure that we put in place to get those real-time data feeds can be reused now by other models. If you want to look at a different outcome where laboratory results and medications and diagnoses could be useful. So we're working right now at the University of Michigan with Precision Health, which is a campus-wide initiative, to shorten that life cycle and make it easier to move things into practice more quickly.
It's more or less like a warm startup for the models. Like the pre-trained model can be used for the other institutions as well.
Oh, you mean across institutions? Yeah, so that's another question. So in terms of how models transfer across institutions, so I encourage you to go and look at our paper from the ITCHE paper, Infection Control and Hospital Epidemiology, because there we actually argue for generalizable approaches instead of necessarily a generalizable model, especially in infectious disease where risk factors can depend on the physical layout of a hospital. That's not going to be the same across institutions. So when you have large hospitals, academic health centers like MGH in Michigan, there's a lot of data and a lot of hospital-specific factors that end up being important to the model. We also have a paper that we published in JAMIA in 2014 that looked at transferring models from small hospitals to large hospitals and vice versa. And the findings, they're interesting. So I don't expect any of my clinical collaborators to be experts in AI, otherwise they wouldn't need me. It's really an interdisciplinary collaboration, and that's why we rely so heavily on them in terms of helping us identify the clinical problems. Does that answer your question? Yeah, so it works. It works both ways. So sometimes I'll reach out to specific collaborators. So if I'm looking for someone with expertise in infectious diseases, or they'll come reach out to me if they have they have a problem, and try to develop a collaboration from there. The infrastructure that we build, I should say, is not my infrastructure. It's really a university-wide resource. And with the Precision Health Initiative, we're working on educating and advertising that, so that everyone's aware that those resources are available.
Thank you very much for the talk. I'm more from the health research policy side of things. I'm taking a course as an introduction to health informatics, and I come across this thing called the CDSS, the Clinical Decision Support System. Are you familiar with it? Clinician Decision Support System?
I mean, that seems like a very general term.
Yes. Well, from what I understand, it's basically a system to help clinicians look through a list of indicators to reach a particular conclusion about
Yeah.
a person's health. Is there some potential for AI in that area?
Yeah, absolutely. I mean, all of the tools that I talked about today, I would call clinical decision support tools, right? The goal here, and the title of my talk, is not replacing clinicians. It's about augmenting clinicians, right? So through support tools that could highlight risk factors. Because at the end of the day, oftentimes when we train these models and we look at the most important risk factors, they're not necessarily surprising. They're things that sort of align well with clinical intuition. For example, the receipt of antimicrobials puts you at higher risk of acquiring an infection with C. diff. But it's the fact that we're able to look at so many things at once that's really helpful. So I think that's one of the key values to having these sorts of technologies available.
So say that, and then I'm going to ask one question, then I think we'll break through.
Okay.
Thanks for your talk. I have two questions. The first one is about transformation methodology. I was wondering if you compare these methods with like normalization of the signal and transformation window to see which one is better.
Yeah, so we do normalization already. So all of the signals get normalized before their input.
And the second one is about intellectual. I was wondering if you compare your model with GRU that has less compared to different
Yeah, so that's a great question. So LSTMs and GRUs are essentially different versions of a recurrent neural network. The approach that we propose isn't specific to an LSTM, so it could still be applied to a GRU. The idea is that you're just relaxing parameter sharing. So there are fewer parameters in the GRU, and you can relax those as well. But because the GRU will share parameters at every single time step, we suspect it's going to have the exact same issues.
So my question, following yesterday's Health AI Deployment Symposium and your comments today, we really all are getting the sense of how much work it is to take even a promising model to the point that it's deployed. And so one of the things that struck me with your I approach is that itself might be a bit of an indicator about where you really might have something to gain when moving beyond those variables or features that experts already recognize as being important. So just your thoughts on that. Could we use it in that way up front, early in the process, to say, is this something that we think ML will add a lot to versus something that experts already know and our model might work but may not actually be that needed or helpful?
Yeah, so you could certainly use I for this. You could also one of the things that we did very early on with the C. diff work was we compared to if we just used a curated set of risk factors, how well did we do, versus if we threw in everything, and where was the gain. And we published that, I think that was a 2014 paper, to show the gain that you get. And it's not just about the gains in discriminant performance, it was actually way more work to go in and curate that set of risk factors. So to map from the literature the list of the precise antimicrobials that were associated with high risk, going and finding them in the EHR versus just taking all of the meds, right? So again, it's a generalizable approach, because now that we have infrastructure to extract data from the EHR and produce features, we can just swap out the outcome, all right? Change C. diff to a different outcome, and you can retrain the model, right? It doesn't rely on you going back and identifying those curated risk factors again. Yeah.
So to extrapolate a little bit, it's not as though that expert knowledge is agreed on even.
Yeah.
So there might be cases where it would actually be more work than anybody thinks to get to the point that you've got the expert.
And I'll highlight one thing that I didn't get to, I skipped over, but a question I often get is, well, can't experts be wrong? Yes, experts can be wrong, and we think it's actually a feature. So one of the things that we did was we looked at a comparison, and there are more comparisons in the paper too, but here we looked at, well, what if we had an incorrect expert? And what we did to mimic that was we essentially randomly permuted R. So R told us what features were available or known. If we randomly permute that, it's as if we're nudging the model towards the wrong thing. And what we show is that you can actually recover from that. So we're not going to sacrifice discriminative performance to listen to incorrect experts. We're going to listen to the data. And the average precision here is low because those incorrect features don't trickle up near the top because they're not important. So this, I think, is a feature that you can use to highlight when what we think we know about a certain disease might be off. Yeah.
Okay, folks, so please join me again and thank you, Jenna.